Hello. So today I want to talk more about properties of Laplace transforms. In my previous video, I talked a little bit about some of the basic properties that we needed in the context of solving differential equations with the Laplace transform. Here I want to talk about not the process of solving differential equations, but just the properties themselves. And in particular, I want to show a little bit showcase a more advanced property of Laplace transforms. So here, to start, I want to review just some basic properties of Laplace transforms. Not basic necessarily because they're easy to prove by any means, or even easy to use, but basic in the sense that to get off the ground solving differential equations using Laplace transform, the Laplace transform, you absolutely need these properties, right? You can hardly do anything unless you have these. So pretty much anytime you're solving using Laplace transforms, solving a differential equation using Laplace transforms, you're going to apply linearity, right? The fact that constants pull out of a Laplace transform and that you can distribute a Laplace transform over different terms in a sum, that happens essentially every time you go to solve a differential equation. Somewhere you'll have to apply the Laplace transform of a derivative, and maybe iterated versions of that to apply it to a second derivative, third derivative, right? You're solving a differential equation, there will be a derivative, right? Laplace transforms especially come up frequently when you're working with piecewise or discontinuous forcing terms, as shown in an example in the previous video, right? So this property comes up all the time. How do you take a Laplace transform of an exponential function, of a polynomial, or of a monomial, which then with linearity can be combined to create a polynomial, or say the Laplace transform of the basic trig functions of sines and cosines, right? So these we use all the time when we're using Laplace to solve differential equations. Then, so what I wanted to do today is I wanted to show a bit more advanced property, one that maybe doesn't come up all the time when you're solving differential equations, but it just to showcase how might you prove a more advanced property and also what kind of utility it could have. So here's an example of a more advanced Laplace property, and this is by no means comprehensive. There's tons of interesting properties of the Laplace transform, convolution, and all these. There are so many interesting properties of this map. I just wanted to show one of them here today. So here's an example of a little bit more advanced property. Suppose you have the Laplace transform of a function multiplied by a power of t, right? So if you have it multiplied by a power of t, it turns out all it does, the way it affects the Laplace transform, is it multiplies by -1 to the n, where n is the power of t, and takes in derivatives of the Laplace transform, right? And here I want to point out something, that notation right there, this is referring to, it's not an nth power, right? It's an nth derivative. So this is the nth derivative. And I also want to say what variable this was with respect to, because here we have two variables, right? We have two independent variables. We have t and we have s. Here it's an nth derivative with respect to s. So just to keep track of what is going on there. So I want to look at how one could prove a property like this. I'm going to start with n equals 1, right? I want to start with the case where n equals 1. If n equals 0, there isn't really anything to prove, right? If n is 0, you're just saying, well, here we can comment. This expression right here, that is the statement for n equals 0, right? That's just the definition of capital F if n equals 0. But n equals 1 is the first case where we have something really to say. So here's what I want to do. I'm going to calculate the right-hand side of this identity. I'm going to calculate and what does that look like? It looks like -1 to the 1, and then the first derivative of capital F with respect to s. Right? So -1 to the 1 Well, that's just them putting a negative sign up front. And then the second expression, what we're doing is we have a first derivative with respect to s. So I'm going to write that as ddS. Then it's ddS of what? It's ddS of the Laplace transform. So here I'm going to apply the definition of the Laplace transform. Right. And I was saying, okay, we're taking first derivative of the Laplace transform, integral function times e to the minus st. Right. Then what I want to do is something that isn't super obvious at all, but it turns out it's valid to do this in most scenarios. And I'm purposely being a little bit vague about what those scenarios are. Say in a 300 or 400 level, or even a graduate analysis class, you study under what conditions is this kind of thing that I just did valid. If you look at what I did, I swapped the order of the derivative and the integral, right? I changed the order of operations there, right? So in the first one, we had see up here, we have the derivative of the integral. Here, we have the integral of the derivative, right? We switched the order of those operations. So why is that valid to do? Once again, it works under most conditions, but it's really a 400 level or maybe even a graduate analysis class, say in measure theory, right, is where you would look at something like that, that if you're differentiating a family of improper integrals, when can you switch the derivative and the integral? So just be aware that there is something being swept under the rug here, right? So under some conditions, these things are equal. But most of the time, for the kind of functions that you're working with, when you're actually solving differential equations using Laplace transforms, doing this sort of thing is just fine. So that's something that we won't open that whole can of worms, but we'll just be aware that there is a can and there are worms in it. So, all right, what happens next? Let's now take ddS. Let's take this derivative. Well, look at what we're differentiating here. Here, all of the variables are t except for that one right there. That's the only s in this whole expression. So everything is constant, right? Everything just is constant with respect to this derivative except for that s. So I'm differentiating an exponential function. So it just stays that exponential function, but I have a chain rule. And what is my inner function? My inner function is minus st. So what is the coefficient on the variable? It's negative t, right? S is the variable and negative t is the coefficient. So this derivative, all it does is it multiplies by negative t. Right? And once again, what is happening there? It's chain rule. Right? It's a good old same chain rule that we all know and love for Calc 1. It's just a slightly tricky application of it, right? You just have to remember that s is the variable, minus st is the inner function, and we're differentiating with respect to s. So what it multiplies by is negative t, the coefficient on s. All right, next, what happens? Well, the negative sign we can factor out of the integral, so cancel the negatives, right? Cancel, double negative, cancel those. And now, if you look what we have, this, if you think back to the definition of Laplace transform, this is a Laplace transform, but it's a Laplace transform not just of f of t, but it's a Laplace transform of t f of t, right? Where f of t usually lives, in a Laplace transform, we now have t f of t. That's our new function. So this, I can say, is the Laplace transform of t f of t, right? And at this point, I just proved the identity for n equals 1, right? And this is what we were trying to prove. This is the left-hand side of the identity, right? So I now know that what? The Laplace of t f of t equals negative f prime of s, right? Well, now what can you do? Now you can iterate this, right? If you iterate this, what would t squared be? Well, I'm multiplying the previous by t. And if you multiply by t, what do? You take a negative and you take a derivative, which gives me this. Now do t cubed. All right, well, multiply the previous by t. So it becomes negative derivative. Oh, there we go. Right. And so on. What's the pattern? Well, we multiply by -1 each time. So in total, with t to the n, we've multiplied by n minus 1s, hence -1 at the end, right? Or just think of it as -1 at the end is how you generate an alternating sign pattern. Also a valid way to think of it. We also have n derivatives with respect to s on our function, right? So this is a proof of this identity. Now, here, if you feel uncomfortable about the and so on, right, you can make this more formal. What's the formal way to do this? Right, if you wanted to see a more formal argument, you would do induction. You would do proof by induction. So what we did for n equals 1 or n equals 0, actually, you could take that as the base case and then do an induction proof, right? So assume that it's true for some arbitrary n, show that it's still true for the next one. At the end of the day, it's essentially equivalent to what we did here. So this is our proof of a more advanced Laplace transform property, right? And what is the effect of multiplying by t to the n on the Laplace transform of a function? It's multiplying by -1 at the end and taking in derivatives of the function with respect to s, right? All right, let's now use this in an example. Suppose you wanted to do the Laplace transform of this function, t cosine t, right? Here, I would not particularly want to do that by definition, right? Because we'd have to take the antiderivative of t times cosine times e, right? That's a heavy antiderivative, right? Big, nasty integration by parts. I really don't want to have to do that. So here's what's so nice. What's so nice is this property. The amazing thing about this property is instead of doing a nasty antiderivative, what do I get to do instead? I get to do a derivative. And as we remember from Calc 1, Calc 2, derivatives are way easier than antiderivatives, right? So there's something really nice about this result, right? Because we're replacing a difficult antiderivative with an easy derivative. It's kind of counterintuitive that it works at all, but I mean, we just proved it. It works, right? So let's take this property and let's say, okay, right, we're going to do this derivative instead. So here, what do I need? Well, I need the Laplace transform of that function without the t on it, right? So Laplace of cosine of t is up here. So I'm going to use this property, right? The cosine of AT has Laplace transform S over S squared plus A squared. So let's do that. In this case, A equals 1, right? So recall that formula, then apply the property that we just proved. And here I want to apply it with what plugged in? I want n equal to 1, little f equal to cosine, and big F is going to be S over S squared plus 1. Right? Those are all the pieces that I'm plugging into this new property that we just proved. So let's carry this out. What do we have? We have the Laplace of t cosine t equals what? Equals -1 to the 1 times the derivative, right? The first derivative, dds, of s over s squared plus 1. Right? Like I said, now I don't have to do this horrible antiderivative up here that you would need if you were going to do this with the definition of the Laplace transform. Instead, I get to do this easy derivative, right? Quotient rule. Right. Square the bottom. Then in the top, we have the bottom times the derivative of the top minus the top times the derivative of the bottom. Combine like terms, right? S squared minus 2s squared. Put the negative through. And we're done, right? So there we go. We just calculated the Laplace transform of t cosine t. There it is, s squared minus 1, right, over s squared plus 1 squared. This is super handy. Now we know the Laplace transform of t cosine t. These are the kind of terms that come up in differential equations, right? This is a t cosine t is oscillation with growing amplitude, right? It's a fairly natural function to consider. And now we know it's Laplace transform, right? But we didn't have to do a horrible antiderivative. Instead, we proved sort of a more advanced property of Laplace transforms. And then once you have that property, it's quite easy to get this Laplace of t cosine t. So, all right. Thank you for listening. That is all for today.